Hello, chemistry students. We are working on acids and bases, and the last time we spoke, we talked about a reminder about equilibrium, just because we need that concept when we talk about acids and bases. And we talked about electrolytes, both strong and weak electrolytes. We talked a little bit about what that means. We talked about non-electrolytes that don't create ions in solution. We talked about strong electrolytes that make lots of ions in solution and weak electrolytes that are in equilibrium and create a situation where there's a little bit of ion in solution so that it conducts electricity, but not as well as a strong electrolyte. So we're going to use those concepts as we begin to talk about acids and bases. And so just kind of, we are familiar with these words, acids and bases. Maybe you're familiar with the fact that acids taste sour. Things like citric acid, any sort of citric fruit, lemon, lime, orange, grapefruit, that citric acid is what's in there that makes them taste sour. You're not supposed to taste acids, but basically those are acids, of course, that you can taste. Vinegar is another example of an acid that you're familiar with that you use probably in salad dressing to give it a little bit of a sour taste, mixed with sweet sometimes. A base tastes bitter. Again, I'm not necessarily wanting to taste bases, but those are the characteristics of those things. An acid is basically a substance that creates H3O plus when put in solution. A substance in water that makes H3O plus. Okay, and we call this particle, we call this hydronium. It is one of the polyatomic ions we spoke about before. I'm going to write this so you can actually read it. Hydronium. It's one of the polyatomics we spoke about early on in the quarter. A base is a substance in water, so I'm going to just put a substance in water that makes hydroxide, OH minus, okay? And so this particle right here, again, is one of our polyatomic ions. Is called hydroxide. So that's kind of a general definition. Substances that taste bitter, substances that taste sour, and then this H3O plus and this OH minus are sort of the crux of the matter. Another way to identify an acid is it's a proton donor. And that basically means that it gives away a hydrogen, okay? A proton donor. So an acid is something that gives away a hydrogen, and a base is a proton acceptor. And so it gets the hydrogen, okay? And so basically it's just this exchange of hydrogen ions that we would dictate an acid-base reaction. Our favorite acids that you're familiar with, we've talked a lot in this class about hydrochloric acid. It's the stomach acid that helps in digestion. CH3COOH is acetic acid. This is just a fancy name to say vinegar, right? And so I'll give you some others here in a second. And then our famous base is NaOH. It's like the poster child base. So we have the poster child acid, right? Hydrochloric acid, and we have the poster child base, that's sodium hydroxide. The poster child weak base is NH3, which is ammonia. Maybe you have smelled ammonia. If you have cats, perhaps you have looked at the ingredients in sort of window cleaners, usually have ammonia in them. Back in the day, you could buy ammonia just in a bottle and it would make your nose sort of, the nose hairs sort of, yeah. Anyway, okay. So a little bit of practice on which of these can be an acid. Remember, an acid is a proton donor. Okay, and so when you look at these substances, right, when we look at all these substances right here, we want to make sure they have a hydrogen to donate. So I'll do a couple, and our regular policy is I'll do a couple and then you do the rest, okay? So this one must be an acid because it has a hydrogen to donate. This one must not be a donor because it doesn't have a hydrogen to donate, okay? And so kind of thinking through those for that. The Bronsted base, remember, it's a proton acceptor. Okay, and so thinking about something that's willing to take on a hydrogen, remember hydrogen ions are positive, so positive things aren't going to want to take on a hydrogen, but negative things might, right? And so when I put HOH together, you'll notice that I get water, and that shows up a lot when we're doing these sorts of things. This is a covalent compound, right? It's got 2 carbons and 6 hydrogens on it, and it's happy, it's satisfied, it doesn't really need anything. And so basically you would not accept that. You would not expect that to accept a hydrogen. So I'll let you do those and finish up those, and I'll get those answers on there when I upload this content to Canvas. Okay, a little bit more about acids, just a little bit more here. I mentioned that I would go over some of the rest of them. So strong acids and what makes, I guess I gotta finish that thought down here at the bottom of the page. Sorry. So big idea right here before we go on, which the strength of an acid or base depends on. So when we say strong electrolyte, okay, we mean it ionizes well, right? It means we get lots of ions. And our example that we used earlier when we talked about a strong electrolyte was sodium chloride, right? So basically a strong electrolyte, if you just replace that word with strong acid or base, you're talking about the same thing. So a strong acid or a strong base is something that ionizes really well. It's going to conduct electricity very well. It's going to create a lot of ions, right? And it's a good conductor of electricity. Okay, if you want to talk about a weak electrolyte, and this is kind of why we talked about this before. Okay, basically we know this is more of a situation where we have an equilibrium. There's fewer ions, right? And so basically it doesn't conduct it does conduct electricity, therefore the name electrolyte, but it doesn't conduct electricity as well. So conducts electricity, but not so well. Okay, so if you replace the word electrolyte with weak acid or base, you have the same idea. So again, when we looked at our picture here of the conductivity of strong and weak electrolytes, right? We actually used a weak acid here. We used that's vinegar, that's acetic acid, right? And we talked about the equilibrium. So if you understand the concept of a strong acid or a weak, a strong electrolyte and a weak electrolyte, then you understand already the concept of a strong acid and a strong base. So let's talk about that a little bit more. So strong acids are our favorite one. Again, there's hydrochloric acid, sulfuric acid, nitric acid. And these just have the property of being good ionizers, right? So these are strong electrolytes. They ionize really well. The bases down here, right? The bases down here, sodium hydroxide and potassium hydroxide, also strong electrolytes. That's what makes them a strong base. When you go to look at weak acids, again, this is just a weak electrolyte. So both of these are the same idea. They ionize, but they don't ionize very well. Their equilibrium favors the reactant side. The products are there, but they're not as many as the reactants. So one way to think about this in a reaction is when hydrochloric acid, which is a strong acid, right, there it is, reacts with water, we said the hydrogen is donated by the acid. So we donate the hydrogen to the H3O plus, the H2O, and we have a leftover of a Cl minus, also aqueous. Okay, so when that hydrogen goes away, it's an H plus that's donated, right? And so our other product is going to be H3O plus AQ, and here it is, there's our hydronium. Okay, so two things, right? Acids are hydrogen ion donors, so this is a H donor, okay? This is a H acceptor, that makes it a base, and we'll get to that in a second. And then when I look at what's left over, once I give that hydrogen away, this is my leftover, and because that hydrogen has a positive charge with this neutral substance, it's got an H3O plus. And so an acid, we said, creates hydronium in solution. And so there it is. There's the acid. Okay. So that's a strong acid. And what I like to do is indicate it by a single arrow going one direction. And we can think about this as pretty much most of the situation. There's this substance there, and there's really none of this left over. There's water in there still, but for the most part, there's just ions. That's what makes it a strong acid, aka a strong electrolyte. Okay, so basically, if we go to this acid right here, this is our weak acid. So we're going to write this arrow as a reverse and a forward reaction at equilibrium. There's the hydrogen that gets donated. Okay, so there's the hydrogen that gets donated. It gets donated over here, so there's our H plus. So what we get left over is CH3COO minus. It's missing a hydrogen, so its charge goes down. And there it is, once again, our hydronium that is created by this acid in solution. What makes this weak, again, is the amount of ion is smaller than it would be for a strong acid up here. And that's the name of the game. Okay, when we do a weak base, we said a base is a proton acceptor. And so here is our base right here. Let's see. Okay, this is our base right here. This is ammonia. And so the hydrogen from the water gets donated this time. So the water actually is acting like an acid, which is kind of interesting. What we get here is NH4 plus. And what we get here, if you think about it, right, if this goes away, I'm left with OH minus, both aqueous. Okay, so a couple of things. We said a base is a proton acceptor, right? It's accepting the hydrogen ion, and it creates OH minus hydroxide in solution. And so there it is. We get to see both of those things happening. So that's what makes that a base. Okay, so basically, when we do these acid-base reactions, we want to chat about these words. There's a couple vocabulary words here that we just got to throw in. We can identify the acid and base, right? The acid is going to be the proton donor. The base is going to be the proton acceptor. So you just kind of look at the reaction and decide, you know, where the hydrogen is going and who's getting the hydrogen, okay? The conjugate acid and the conjugate base, right, are the same thing. We just give them a different name because they're on the opposite side of the reaction, okay? So the acid, again, is going to be the donor and the base is going to be the acceptor, but it's on the opposite side of the equation. So if I look at these two reactions, I'm going to key in on this one right here with the vinegar and this one right here with the ammonia. And basically I want to look at this and go, all right, who's doing the accepting, so we know that this is the acid. We know that this is the acid because it donates a hydrogen. We know that this is the base because it is accepting the hydrogen. So that one, I hope you get there. So when we look at the reverse reaction, we want to scrutinize that as well. And what you might notice is when it goes backwards, this hydrogen gets donated to this is called an acetate ion. So that makes this the conjugate acid. We just give it another name just so we can distinguish them from one another. And that makes this the conjugate base. So still the same idea. The acid gives away the hydrogen, the base accepts it, but this time it's looking at the opposite side of the reaction. So we can do the same thing on this, the ammonia and the water. We know that the water is the acid this time, which seems kind of weird to say, but it's donating a hydrogen. This is the base, okay, because it's accepting the hydrogen. And then on the other side of the equation, for the reverse reaction, which I forgot to put in there, who's donating the hydrogen? Well, this is donating the hydrogen back. So when I look at this and this, I'm kind of looking across the arrows to see who's getting and who's getting. So this is and the acid because it's giving it, and we call it the conjugate because it's on the other side. And then this is the conjugate base because it's accepting, conjugate base. So that's the game, okay? And I'm going to let you guys practice that, okay? So we want you to practice getting, and so practice looking at across the equal sign, right? So who's getting and who's getting. So this is an acid-base equation or reaction, and you're going to, in this case, I'm going to help you that this is going to be the one that donates the hydrogen, and this is going to be the one that donates the hydrogen. So I'm kind of keying in on that. So you're trying to look across the equal sign here and figure out who's getting and who's giving, what the products are. And then I'll challenge you on this one to identify the acid-base pairs. And that means basically the acid base and the conjugate acid and the conjugate base. So I'll let you guys do that, and I'll put that up in the notes for you. So I'll let you practice that one just to kind of apply that concept. Okay. Again, here's more practice on the same thing. I'm going to let you guys do that too. So basically, I'll talk about this one and then we'll write the Ka. So I don't know how many of you guys have been stung by an animal, a creature like a bee or an ant, but it's formic acid that does that. And that substance is I'll write it bigger in black, HCHO2 plus water, basically. It's an acid and it's weak. So we're going to write an arrow that goes both ways. This hydrogen gets donated to the water. So I'm going to get CHO2 minus plus H3O plus. This is liquid, and all of the others are going to be aqueous. AQ. So what we want to do is we want to write an equilibrium expression for this. And that's exactly what we talked about before. We talked about that earlier in this lecture where we talked about what K is. Remember, it's products over reactants raised to their coefficient. And so that's the same thing. I'm going to do A down here so I can write it out and not have too much mess on here. So I'm going to write it as a Ka. Okay, and the only reason I'm calling it a Ka is because it's an acid equilibrium. It's an acid equilibrium, okay? And so when I write this, I'm going to write my products, CHO2 minus times H3O plus, over my reactant, HCHO2. This is a balanced equation, so I don't have to worry about the superscripts because all of these coefficients are 1. And I'm leaving out the water because it's a pure liquid and its concentration doesn't change. So that would be my Ka value for this acid. And what we know is this Ka value is pretty small, okay, because this is a weak acid. And that means that this equilibrium is going to not have very many products and have mostly reactants, right? And so when I look at this equilibrium and I analyze it, it's going to have more of this, my reactant, than it is going to have of my product, right? And so my product is not very much. That's what makes it a weak acid, okay? So basically that's what I'd like you guys to do, and identify the conjugate acid base. So write the equilibrium expression and identify the acid base and the conjugate acid and base. We know this one is the acid. We know this one is the base. It's accepting it. And the opposite side, right? This is the conjugate acid and this is the conjugate base. I will try to point out, I don't know if this is going to make sense to you, but I'll try to point out that they operate in pairs. You'll notice that this is the acid on this side and it's the base over here. And then this is the base on this side and it's the acid over here. And that's why we call them acid-base pairs. So that's one way to identify it. Okay, I'll let you guys play with B and C. I will put those up for you. And I really appreciate your attention. Thank you so much. Next time we get together, we're going to talk about pH. Okay? Have a great day. Thanks for listening.